we did used to play with marbles.
Wow, isn't that great? Because that is something that I thought it was gone because it was an age. My son, which is probably a bit older than you, never marveled. What are those? You never, and that's okay, you know. But well, the idea is that you can get all the marbles in this cloth thing here at the back, and you actually put them all inside. And you just tie them up here, and you would say, what is the volume of the thing that it sticks up here? How is that related to the number of marbles inside? It happens that each one of the marbles has a definite volume, so the total volume, there's some empty space in between, but the total volume should be proportional to the number of items that you have inside, and you pack them to form a ball or something like that. When you do that, you find out that you know, this is what I'm saying. The total volume is proportional to A. A is the number of marbles inside the bag. So the volume is of each one of the balls is 4 pi r naught cubed times 4 over 3 pi r naught cubed times A. And this thing here should be, this is the volume, and this should be a constant time A. So this is a way to think about it. And the constant here, it happens to be, if you look at actual nuclei, you can actually get that this constant here is 7.24 Fermi cube. When Fermi cube is 10 to the minus, is essentially 1.2 times 10 to the minus 15 meters is the value of R naught. Okay, so this is the way to think about a nucleus. Is just, you know, a bag of marbles essentially. You know? This is the first relevant thing. Now the size is really very important, and the energy scale is also very important. The energy scale of the atoms, the excitation energy between the difference between an atom being in a particular energy scale and getting to a different energy scale, that is of the order of electron volts, 10 electron volts, 5 electron volts, 2 electron volts. Those are the energies. It has to do with the difference in energy, has to do with the wavelength of light or something like that we actually see. Okay. The energy scale for neutrons and protons inside the nucleus is mega electron volts. Okay, so it's 10 to the 6, the other value. So if the energy of the atoms is electron volt, the energy of the nuclei are mega electron volts, 10 to the 6 electron volts. Now you can understand why people are so concerned about this this type of energy devices that we have, because the energy that you get from electron volts, it's like the one you get from fossil fuels. You know how many liters, but each hydrogen and carbon bond that you break, you get a few electron volts out. Okay, what do you do for a single reaction that involves a nuclei? You get of the order of mega electron volts out. Okay, we're gonna get probably next lecture into more details about how this number works out. But this is the main difference. If you have a burning reaction of a fossil fuel, you get electron volts for each one of the reactions. If you get a nuclear reaction, to get an energy, the energy you get out is the order of mega electron volt for each one of the reactions. So that's why the intensity of the energy inside the nuclear matter is so important, and it's so relevant in many aspects. We have never had in Chile nuclear power or anything like that, but there is something, it's really of concern for global security. And so we should somehow understand what is the origin for this energy around. Yeah? Well, to tell you the truth, this is the energy inside the atoms. It's an option to global warming. You know, it's not renewable energy, but it's also not producing CO to the atmosphere in order to get some. Okay, so there could be a trade-off at one point in nuclear energy. In particular, if there is no radioactive residues at the end. Okay, if you can have a clean nuclear reaction that produces no residues at the end, you could actually, this could be a solution, like the sun, like the energy coming from the sun, to solve the global warming problem. In a neutral atom, there's one electron for every proton. So the structure is the following. You have inside here, you have the nucleus of the atom. The nucleus of the atom has Z protons. Each one of the protons inside has a charge that is positive. The positive charge inside the nucleus is balanced by the cloud of electrons around it. Okay, so you get a neutral ball, which is an atom. But inside the nucleus, you get the bare C protons, and actually the protons repel each other. So in order for these guys to be bound together inside a nucleus, you need some different force. You need a nuclear force. Okay, that's what binds them together. And the good thing is, to make this guy stable, you actually have to put something that has the attraction of a nuclei, but doesn't have the repulsion of a proton. And those beasts are the neutrons. There's a particle almost like the proton, but with no charge. Okay. So in terms of units, again, the mass of the proton is almost 1 atomic mass unit. The mass of the neutron is, it's almost 1 in atomic mass unit, but it's a little heavier than the proton, meaning this guy is low mass, this is a little bit higher mass. And then there is the electron, which in terms of mass unit, the electron is 511 kilo electron volts. In terms of mega electron volts, it looks like that. It's 0.55. In terms of mega electron volt divided by C squared, these are the units. So here is more evident that the neutron is about 1 MeV heavier than the proton, and then the electron, which is almost negligible. So there's an important language we have to start to define here: the isotope. What is an isotope? The problem is the name of an element in particular has to do with the Z, the charge of the proton. Okay, helium is 2. Okay, and what does it mean? That it has 2 protons inside, and it has 2 electrons on the outside the neutral particle. Okay, so if I change the number, but I could actually increase the number of nucleons in helium, and or decrease it, and I will get a different particle, but it will also be helium. Okay, most of the chemical properties will be the same, because the chemical properties are somehow related to the electronic structure, and the electronic structure is almost the same in the case of, let's say, a helium with 1 neutron, or a helium with 2 neutrons. The helium with 2 neutrons is helium-4. That's the way it is. I'm labeling it by the number of nucleons inside. So helium has 2 here protons and 2 neutrons. Okay, and helium-3, which is used for lowering temperature actually of helium, meaning the liquid temperature of helium is different in helium-3 and in helium-4, and it's slightly different. It's not a big difference. The chemistry is almost the same. Yeah, that's what I'm saying. When you change the number when you change the mass of the nucleon, you almost don't change the electronic structure, you just change the mass of the whole thing, okay? And so what you would change if you do that is you will change the vibrational properties if you add a neutron or remove a neutron from a system, okay? So this is an isotope. Helium-3 and helium-4 are nuclei that have 2 protons. One has 4 neutrons in total, meaning it has 2 neutrons, and the other one only 1 neutron. Okay, but it has the same number of protons. Those are they are the same nuclei, and they are called isotopes. Those are isotopes of the same nuclei. Okay, so this is a Bernoulli language. Another important property of the nuclei is the total angular momentum that the particles can have. Okay, here we have to get into a model. What do this thing will have angular momentum? You can imagine this soup of marbles in the sac there, which is the nuclei. They can actually be rotating inside. Each one of the particles in there, the proton and the neutrons, are fermions, and as the electron, they have a spin and a half. So you have A particles inside, and they can all have let's say the angular momentum aligned. So you just sum them all up, and the total angular momentum of this ball, which is the nucleus, would be the sum of all the spin inside the nucleus. And this thing is almost like the atom in a way, meaning it doesn't have a potential that goes like 1 over r, but it has a potential that is almost I would say an infinite box, or a very deep box where the nuclei live inside. But it is a spherical box, so it is symmetric in terms of the the dimensions. It's symmetrical. It's spherically symmetric in space. Okay, so you can say that if you solve the Schrödinger equation for a nuclei, well, you have to change now the mass. It should be the mass of the proton, the mass of the neutrons that go inside, and there's going to be a very strong attraction that has to do with the nuclear interaction. But those guys can move inside this potential that we have created for them, and we generate orbital angular momentum. So you can have a total angular momentum of the particles in the nucleus being the sum of L plus S, which is J. Okay. If you now take this guy and put them in a presence of a magnetic field, you will see a splitting of the levels, as in the case of the electrons. With the difference now that when we study the electrons, the expression from the Bohr magneton is the same as this one, is EH divided by 2 times the mass of the electron. But here we have to divide by the mass of the proton. But these guys, the mass of the proton respect with the mass of the electron is 2,000 times higher. So the protons is much heavier than the electron, even though they have the same charge, the mass of the electron is much heavier. And how do we get this? Well, this is the actual scale constant that produces the difference in energy induced by placing a neutron or a nucleon in general in a magnetic field. So this is called the nuclear magneton, okay, which is actually much smaller than the Bohr magneton. This is an order of 10 to the minus 3 smaller. Why is that? Because the mass of the proton is 2,000 times the mass of the electron. So if I plug this thing in here, and this was the Bohr magneton before, 5.8 and 10 to the minus 5. This is 3.15 times 10 to the minus 8. So it's a very small number, okay? But it's very useful actually, and you'll see why. The magnetic moment of the proton, the magnetic moment of the electron, if you remember well, is simply the magnetic moment of the Bohr magneton divided by not divided by anything, divided by a half, because it's a product, and multiplied by G. G is the geomagnetic constant. So it's G times the modulus of the magnetic moment times the Bohr magneton. So that's the magnetic moment of the electron, with a minus sign because it has a negative charge. In the case of the proton, they both have this strange number here. So it's not exactly the nuclear magneton as in the case of the electron, but it's about 3 and this is about 2. Okay, so the magnetic moment of the proton is a bit larger than the magnetic moment of the neutron. The proton, though, it has, apart from this magnetic moment, it has electric charge. So we can use this to induce what is called nuclear magnetic resonance. The energy of a proton placed in a magnetic field will be, the energy U is minus m dot b. That's the energy. If you put something that has a magnetic moment in presence of a magnetic field, you have a magnetic field, you have a magnetic moment on this thing, and what will happen if the magnetic moment is oriented in a way that is parallel to the magnetic field, that will be the minimal energy. So there is a dot product associated with that, and the dot product is this one over here, is minus the magnetic moment times B. So if the magnetic moment is aligned with B, you will get minimum energy, and that's what the minus sign means. Okay, you will minimum energy with both things are aligned. Okay, so if you apply a magnetic moment to a nucleon, a proton, for example, this is B equals 0. You have this energy state that is produced by the whatever nuclear system you have. If you, this is the energy of a proton inside the nucleus, and then you apply a magnetic field, and then you have this energy being split in 2 levels here. That has to do with 2.79 the nuclear magneton, and you get a splitting here. You get when you get this energy, the actual, you have 2 values of the spin of the proton. It's plus a half and minus a half. There's this is the form of the interaction. You need to put the spin of the nuclei here too. Okay. There's something missing in this expression. I'm going to fix it when I put out the lecture. So this thing is, you can have the spin of the proton align or counter align to the magnetic field, and in that case, you get, from this level, you get 2 levels, and the separation is simply 2 times 2.79 times mu sub n. Mu sub n is this, the nuclear magneton, times B. Okay, 2 is because it's the difference between 0 and that one. So you add to the ground state mu sub p times B times a half. Okay, and you get there. This is the 279 that's coming from here, from the nuclear magneton, and then you get the magnetic field. The bigger the magnetic field, the larger the difference. Okay, so the difference between these 2 states is proportional to the magnetic field. So let's say protons are placed in a 2 Tesla machine. We have a region where we put, you know, an intensity of 2 Tesla, and they have an energy splitting equals to that thing here. What is the energy splitting? It's very small in electron volt. It's 3.5 times 10 to the minus 7 electron volts. Okay. But what I can do that, I can imagine that between this state and this state, I can actually shine a photon and make a transition from the low spin state to the high spin state. Okay. And how do I do that? Well, I said simply this energy difference here is equal to H nu, and I calculate nu. Nu for this guy is 84.7 megahertz. It's like a radio, you know, like an FM radio or something like that. So this is neat, meaning we can actually detect the position of a proton inside a system. If I just simply, you know, let's say I have a radio frequency here exciting a region where I have a lot of protons that are placed in a magnetic field. At the beginning, I assign the magnetic field to be 0, and I measure what is the intensity of the radiation produced by this coil here with this power supply that goes through the region where I have the protons. Okay, I have a glass bottle with hydrogen inside. Okay, and if I do that with 0 field, almost everything will go. Almost all the radiation generated here will go in. Okay, will go through the bottle and get in here. But when I apply a magnetic field, which is in this case, I said 2 Tesla, for example, and I put 2 Tesla and I tune this, the energy of this guy here, the frequency I can change. You can see that the transmission, if I vary the frequency and I install 2 Tesla here, the transparency of this thing will be almost perfect unless you get to 84.7. When you get to 84.7, you will start inducing, when the frequency gets to 84.7, you will start inducing transitions between these 2 levels. When you induce transition between these 2 levels, the radiation is not going to get through. It's going to be sort of, you're going to absorb a photon and lift a nuclei from this level to that level, meaning not a nucleon, from this level to that, in this case, a proton, from this level to this level. So you will get that an important absorption of the energy at 84.7. Okay. Usually the machines that actually do that generate the pulses that has 84.7 and they send pulses in, because you can actually see this lowering, and it's also an important information to detect how the energy decays from this state to this state over here, because you have an excited state that goes to this low energy state, it decays in this direction and emits photon, and you measure the lifetime of this decay, and you get some important information about the nature of the of the chemistry of the proton, really, or where is the proton located inside. What I'm just describing is this this phenomena of nuclear magnetic resonance, which is used widely used to make images, and it's absolutely harmless, meaning because the frequencies that are involved, this is harmless than X-rays. X-rays are really not great. They're not bad. Let's not get scared by this, but it's ionizing radiation going through your body. There's no ionizing radiation when you do an MRI, okay? An MRI is magnetic resonance imaging, and note that they dropped the word nuclear, yeah? Because before it was called nuclear magnetic resonance, and people got scared. There's something nuclear about this, so I shouldn't get that exam done. It's actually safer than doing an X-ray, by the way. Okay, as I have just described. So how does this thing works? Essentially, when you don't have a magnetic field, the nuclei, the magnetic moment of the nuclei are of the protons are randomly oriented in space. okay? Then what you do is you just put a strong magnetic field, and these guys are strongly aligned, okay? And if you actually you go from this rotation, and if you put a radio signal that has the right energy, you can actually flip the spin. What is the right energy? Well, is the energy difference between that and that. So you can align the spins, perfect, and then you can flip the spins by shining in a radiation. And this is, you know, this is the frequency of the radio. So it's a radio frequency. And so you get your spin in the system aligned, and you get this radio frequency, and you somehow you stop the frequency, and the spins on the protons will realign with the, you stop the incidence of line, and they will realign. The way how fast this thing realign gives an important information about the surrounding chemical environment of the protons. And you know, this realignment, it means, again, this is not the incident radiation that goes in, but now there's radiation coming out by the decay of the excited state. The excited state was here, and it comes down here. That's what happened with the system. How does it work? You actually can get imaging resolution just by changing, by putting an object with a gradient of magnetic field. Okay, so this is how an MRI machine works. You have a big main coil that supplies a uniform field. You need a big B somewhere, okay? And then mounted on that big B, that in this case is something that goes right through your body, because this is a complete big coil here. And then you have smaller coils like that and like that change the energy, you know, that induces a gradient in this direction and in that direction. So essentially, when you put an object, here's an object of a guy in there, and you actually place this guy in here with different, in the presence of a gradient of magnetic field. So in each spot, one by the other, you will have a different magnetic field. A particular magnetic field will mean that the difference between these two states will be certain value, and a little to the side will be a different value. So by discriminating the frequency that actually this thing can make resonate the intensity in each point, you can actually differentiate the location of this of the object inside this machine. So in this way, you can get this really, you know, you can reconstruct 3D images from this thing, because you can actually place, you can locate the exact position of a point by simply resolving where that point is physically located inside this machine. And you know that because you have generated a very important gradient of the field inside the machine. So each point in the individual that is lying there has a different value of the magnetic field. So each particular point of that will generate an image that is different. The only thing that I need is reasonable detectors to actually detect frequencies like this, which is not very complicated because this is essentially a radio, okay? The frequencies that the people have to actually detect are radio frequencies. And they do it with high quality machines that you can get this enormous image resolution that they have today, okay? So here's the whole geometry. You can go into the details of how do they generate the gradient, because if it is a uniform magnetic field, it's no good. You need a gradient. Okay, I don't know how large the gradient should be, but the usual machines, they are labeled by the maximum magnetic field that they have. So this is a 1.5. 1.5 is a 1.5 Tesla machine. Okay, so that means that, you know, this splitting here is less than this. So it means that the frequency of this guy is probably, you know, 60 megahertz or something like that. Okay, characteristic frequency. And then the small gradients, you really have to be very good at designing this added coils. That they're usually superconducting coils. That's why you need liquid helium for these machines to work properly. Okay. Okay. So this is the positive and not harmful part of nuclear structure that provides useful information about living things. Well, everything can be, you know, anything that can have the possibility of storing energy can be used in the wrong way or can be used in the right way. Okay, this is the right way. You get information out of the energy. Okay. Okay, let me. Let me stop my video. It says that I have an unstable signal. Let's go to binding energy of a nucleus. Okay, so what I have here in this expression, it's Einstein formula of masses at its best. Okay, this is what it says here. Look, when you have a certain nuclei that has a certain number of nucleons, A nucleons and C, this is an atom, not a nuclei. This is an atom that has C electrons, C protons, and has A nucleons in total. And now you want to split them, to separate it in each one of the components. What do you need to do? Well, to split them, you have to get something out of it. You have to take it away from inside the nucleus. So how you do that? You actually have to deliver energy to it. So you put enough energy to it to separate it in all of the pieces. This is what I'm showing you here. So you need to put an energy in. So this expression here says, look, the binding energy of material made out of A nucleons and Z protons it's not a material. It's an atom with A nucleons and C protons and C electrons, and you want to separate them in each of the parts. You have to deliver enough energy to actually transform that thing into N times the mass of the neutrons times C times the mass of a hydrogen atom. Why do I say a hydrogen atom here? Because, well, I want to count together. I should actually write here C mass of the protons plus C mass of the electron, okay? But the mass of the electron and the mass of the proton are roughly C times the mass of the hydrogen atom, okay? So this expression is simply the following thing. Let's say, and this is what I'm trying to explain to you now. We have this particle, this atom that is formed by the electrons, which is the sort of pinkish thing around each one of the Z protons that I have here, and then I have the neutrons. Okay, these are the parts of these atoms formed by A and Z. Okay, so here I have A nucleons inside. Perfect. I have the Z protons. The same with the crosses inside are the protons. The ones with nothing are the neutrons, and the electrons are the same electrons that I have here that are sort of surrounding the total nucleus. What is the difference between this and this? Well, for getting from here to here, what I have to do is put a lot of energy here, meaning put a lot of energy to the nucleus to actually split it like that. If these guys, get together spontaneously and form this thing, a lot of energy will be delivered because of that. This is the key thing that one has to understand, okay? So this expression over here, the difference between these two things is this expression here. So this, it makes very evident the difference in mass is equivalent to a difference in energy, okay? So my question here is, let's say I have here one atom of helium-4 in a balance, and I am measuring the mass. And then on this other side here, I put 2 protons, 2 neutrons, and 2 electrons, which are exactly all the components in helium-4, but here they are completely separated. So the question is, what would the balance show? Is the balance showing a higher number here or a higher number here? Okay, which one is heavier of the two things? The fact is that the difference between these two guys is the energy. So I have to. So this is a lower energy state. If I actually give enough energy to this, I get this thing. So it means that this guy, since to get this, I have to provide energy in here, and energy is equivalent to mass. The energy that I have to provide in here make these guys heavier. Okay, that's what it is. So this is having everything separated into components has a higher energy than having them forming a nucleus and being like that. Okay, the difference in energy here is exactly this. That is the binding energy. What I'm actually reading here is what it's in here. So in this particular case, what I have here is this is exactly the same expression. Here I have the mass. I actually wrote this guy on this side only. Yeah, I have the mass of the nucleon here, and I have the mass of the components here. But as you can see, this guy, you have to add this piece to get this mass. So this is a lower mass. The helium atom is a lower mass than having the hydrogen and the proton isolated on top of the balance. This experiment cannot be done. It's just a way of thinking of things only. So the difference in between the energy of all the components and the thing forming a nucleus is what is called the binding energy. And that is a very sort of relevant aspect of this is a very relevant aspect of nuclear energy. And you can see that definitely the difference between these two masses here, or collection of masses, it's on the order of the mega electron volts again. Okay, let's look at this table here that shows the binding energy per nucleon for all the stable nucleons on the periodic table. Okay, so in global, it looks like the binding energy is almost like, something like, on average, like 8 mega electron volt per each nucleon inside each. In order to actually find out what the binding energy of a nucleus in particular is, what is the energy that I have to give it to split it in all the parts, it's it's this number. Let's say in this thing here is 8.8 in the case of nickel, which is the highest number in this scale. This will be nickel times. I have to multiply 8.8 times 62, because that will be the energy that I require to actually separate the nickel constituents in each one of the parts. I mean, I will have 28 neutrons, and the difference between 62 and am I doing this right? Oh, no. I'm doing it wrong. This is the Z. What goes here is the Z, okay? So essentially I will have 20, if I give this product of energy, 8.8 times 62, I will have 28 hydrogen atoms, the difference between 28 and 62 neutrons lying on the table. How can I get that out of a nickel? Just deliver to it the energy of 8.8 times 62 as measured from this curve here, okay? There are very significant points here. One of them is this is a very stable nuclei. Actually, this is helium, which has a peak of stability here. This here is deuterium, because it's hydrogen with two nucleons, one proton and one neutron, and over here is uranium 238. The particular shape of this curve of the binding energy like that has a minimum here and also come back here like that. We will get to see this in the next lecture in more detail, but there is an advantage of actually getting this nuclei and split it, okay? You will gain energy. You will deliver energy, because if you go in this direction to the maximum here, let's say you take a 238 nuclei and divide it in two, you will get out of that division you will get energy. So essentially this guy is going to be an advantageous thing to actually divide and get to a region around here. For this nuclei over here, it is advantageous to actually form something else. To hydrogen, for example, it will be good to have this guy reunite with another deuterium to form helium, and it will gain this amount of energy. This process going this direction are called fission processes, meaning processes that divide heavy nuclei. Processes that go this direction, they are fusion. Fusion means you fuse together, you form a higher Z number, a higher A number nucleus, and by doing that, you gain energy, okay? This is the way, this difference in energy between this guy and this guy is the way the sun works. So this is the fusion energy in the sun. And this difference in energy going this direction is how the nuclear reactor works, okay? So this curve over here, understanding the binding energy per nucleon, it's important to understand nuclear reactions. So this is sort of my justification. You know, we're going to get back to this part of the argument here. How come you can get energy going in that direction and going in this direction from nuclei in this particular table, okay? So that was not my question. My question was here is, what is the energy we need to separate the helium-4 atom into 2 hydrogen atoms and 2 neutrons, okay? So I go here into this table and I read the number of the binding energy per nucleons, and I read 7. Okay. So what is the energy? Well, the number will be 7. Is A sub the binding energy per nucleon will be 7. It means that the total energy, since A is equal to 4, it's going to be 28 mega electron volts are required to split the helium atom. Okay. To resplit this guy and form something else. Okay. That's essentially what it is. I probably should make a comment here, since I was talking about fusion. Why don't all the deuterium in the world fuse together to form helium-4, and and that will be much more stable? The question is, they have to get close together to do that. They could fuse if they can get close together, but to get close together, they have to overcome something else. What do they have to overcome? This is it's a charge 1 particle, and it has to overcome the charge 1 particle together. 2 positive charge, you have to get them closer together to what range of distances? To the order of 10 to the 15 meters. To do that, you need quite a lot of energy, or the particles should collide with in front of each other with quite a lot of energy in order to break the repulsion barrier created by the Coulomb interaction and get close together, so the nuclear interaction become important, and they fuse together and they form the helium atom. That is exactly what happens in the sun. So why does it happen in the sun? Because the temperature in the sun is very high, so the particles can acquire very high kinetic energies, so that process can go on. Okay. And could we do that on Earth? Yeah, but we have to be able to generate something like a little sun, because it's not going to be a big sun, a little sun in in a controlled environment, so that the thing doesn't destroy all the machines around or something like that. So this is going to be a very powerful thing if anybody one day can do it, generate the fusion process on Earth. And the key advantage of it is that it's clean energy. You get no CO2, no radioactive material, nothing. You get helium out of it. Okay, so it will be just beautiful. Okay. So so what I'm trying to get at is this is something very important that has something to do with nuclear reactions and any other properties. So in the next view graph, what I'm going to try to do is actually try to convey an idea of how to predict a model that will give this sort of dependence. Okay. What do we need to know about nuclear forces? The nuclear force does not depend on charge. Okay, so the nuclear interaction between 2 protons is exactly the same as the nuclear interaction between 2 neutrons. Okay, so whatever fields the nuclear interactions are the particles that are inside the nuclei. What are those? Those are protons and neutrons. You can get an electron inside the nuclei? Yeah, well, you could. But that electron will not feel the nuclear interaction. The nuclear interaction is something that happens between protons, between neutrons, and between protons and neutrons. That's it. That's the nuclear interaction. Okay. So these are the strong forces. So the type of particle that feels strong forces has really sort of they have a very specialized character, and other type of particles like positrons and electrons don't feel the nuclear force. So this is the first thing. Neutrons and electrons, and it doesn't have to be, I'm sorry, neutrons and protons and neutrons, and it has nothing to do with charge. Okay. Nuclear force has a difference with electric force. It's always attractive. Yeah, it's an attractive. It's much stronger than the electromagnetic interaction between nucleus. Okay. The thing that I didn't say here, it is much stronger than electromagnetic, and it is limited in range. You know, the nuclear force is not the electromagnetic force. The electromagnetic force, when you draw this diagram of electromagnetic potential, that you can draw a potential that goes up to infinity, and you have your, you know, electromagnetic professor says you bring this charge from infinity. But why from infinity? Because there the potential is zero strictly, and not anywhere else. Here that doesn't happen, because the nuclear force, it's only happening in the range of 10 to the minus 15 meters. So if it goes beyond that, it's absolutely zero. If you get close to somebody, you know, let's say you are charged with electric charge, and you get close to somebody, you know, there will be an interaction between you and that person. You will be attracted or repelled depending on the charge the other person has. But you can get very close to a person, but you're not going to feel the nuclear interaction between you and that person, because the nuclei really have to get very close together. You have to go beyond the electronic cloud of the material to actually see the electronic the nuclear effect of the reaction. Okay. There's also a very important other thing, is that I should have written here that can I do that? I guess I could, you know, I could say, okay, yes, okay. So I want to write here short range. Okay, this is very important. Okay. It didn't come out. No, this is not range. You'll get the point. I'll fix it later. Short range. It's important to write something up here so I will remember what it means. This, I think there we go. Okay. So this is the important aspect of the nuclear force. The strength of the nuclear interaction decreases when the number of interacting particles increases. Meaning, when you put a charge and you put one other charge here, you say the interaction is Q times divided by 4 pi over r squared. If you put another charge at the same position, you say the same Q is the interaction with this charge here, independent that there is other charge that's feeling the same interaction. This doesn't happen in the case of nuclear interaction. Then the nuclear interaction saturates, meaning I somehow screen the nuclear interaction by putting a particle close to it. So I cannot put many particles you know, interacting with one of them. So the nuclear interaction is sort of a pair or three, or a collective interaction that doesn't go to very high numbers. So this is the meaning that the nuclear interaction actually saturates, because it depends, the intensity or the strength of the nuclear interaction depends on the number of interacting particles with a particular nucleus. Okay. Ah, here it is. I shouldn't, you know, nuclear forces are short range. Okay, so we're gonna sort of get rid of this. It's already in there. I thought I had forgotten, but that's it. Okay, now this doesn't mean anything. They are short range, 10 to the minus 15 meters, and only occurs between neutrons and protons. Between neutrons and neutrons, and between neutrons and protons. It means among themselves. Okay. Electrons do not feel the nuclear attraction. Okay, that's something very important. Interaction between a pair of nucleons tend to couple particles of opposite spin, protons and neutrons. So essentially, the nucleons inside a nuclei will, you know, if you look at them, they will try to find themselves coupled together in this way, forming a pair of protons with the opposite spins, or a pair of nucleons with opposite spins. And actually, the most common thing is finding something like an alpha particle. An alpha particle is something like this that has two neutrons and two protons, which looks like a nuclei of a helium atom. Since this thing is actually has a very high binding energy, you can, in the soup of balls inside this bag that represent the nucleus, you can actually find sometimes something that looks like an alpha particle, or the nuclei of a helium atom, which is essentially an alpha particle, inside a nucleus, despite the fact that the nucleus sort of kind of interact, they sort of move kind of freely inside, but they tend to form pairs, and they also tend to form these other structures, which are the alpha particles. Okay, that being said, let's go to find out a way to actually model this curve. And one simple model is it's called the liquid drop model for the binding energy, based on a model based on molecules inside a drop of liquid. Okay, that's why it's called the liquid drop model. Yeah. So let's analyze each one of the 10. If all the nucleons could have the same number of neighbors, let's say we in a nuclei, you say, okay, each one have the same number of neighbors. It means that the binding energy should be a constant, should be the same for all the nuclei. You have the same binding energy. If you want to separate them all into pieces, you put the same amount of energy and they will all go and separate. So this is the first term that you can actually say about the binding energy. The binding energy is proportional to A. If all the nucleons could have the same number of neighbors, but we know that that's not true. Why not? Because this is probably true for 2 or 3 or 4 guys inside the nuclei, but the guys that are in the surface of the nuclei, they don't have the same number of neighbors as the guy in the side, because this guy has no neighbor that way. Okay, so we can correct the number that we have just proposed by something that is proportional to the surface, because the surface area of the nuclei it's proportional to the number of particles in the surface, obviously, yeah, because they have a finite size. So this is what I do. So I got the binding energy before. I recognize the first term, but by now I have to correct this term by something that is proportional to r squared. Why r squared? Because the surface area is proportional to 4 pi r squared. And this is proportional to the number of nucleons in the surface. Okay, but r a is proportional to r cubed. So r squared is proportional to a to the 2/3. Okay, so the binding energy now, I can write it as a function of a, as a constant time a, this one, this is the thing, they are all equal inside. No, they are not all equal, and I correct that, and I put this energy term now, the surface correction. Yeah. Then I said, look, wait, you know, I don't turn off the electromagnetic interaction of the protons inside the nuclei, so that I have to consider the electromagnetic interaction and correct somehow this binding energy that I'm saying here. Why? Because when I have 2 protons very close to each other, they're going to repel like crazy, and that will put, you know, the energy up. How far up? Well, the energy of a particular interacting with 1 proton with all the rest. 1 proton with all the rest will be E² divided by C - 1. C minus 1 will be the energy of all those guys, divided by 4 pi epsilon naught r. So r will be the distance between this particular proton and the C minus 1. And I would say, let's do the same thing for each one of the protons. So I have to multiply that by Z times. So this here is somehow something that looks like the interacting energy of all the protons inside the nuclei. Okay, so I have an expression for R and I have an expression for C. So the expression for R is simply here. See, if I need R, it's A to the 1/3. 1/3 is R. So here is A to the minus 1/3 because it's down here. And then this C times C, that's how they go. And all the rest of the things I piled up in the constant. So here I have a constant, here I have another constant. And what I would do then, I will, find a way to determine this constant based on observations, okay? The other one is the CN symmetry. Nuclear have a higher binding energy if the number of protons is equal to the number of neutrons, okay? This is very much true for low values of Z, okay? So one way of writing a contribution like that, it will mean that, okay, so if A is not equal to Z, the binding energy of that should be lower. Perfect. So I add a term which is proportional to this difference. Let's say C is equal to N. Look, A minus Z is equal to N. And A minus C is N minus Z. This term here is equal to N minus Z. Okay, whatever I have in here is equal to the number of neutrons minus Z. And I wrote it this way because it's more convenient. I'm writing everything in terms of A. And actually, I'm not interested in the positive difference or the negative difference. So that's why I raised the whole thing square. Okay. So if N is equal to C, this term here will be exactly 0. And I have not to discount anything to the energy. So at the binding energy. So this will be the highest binding energy will be in the case that A is equal to 2Z. And that happens only when N is equal to Z, okay? If that is the case. So this term here somehow takes into consideration that there should be a ZN symmetry on the stable nuclei, and we have this contribution. So C equals to N has a higher binding energy. The other one is the pairing of neutrons and protons, meaning see, if Z and N are even, that has a higher binding energy. If C and N are odd, that has a low binding energy. So you want the nuclei to be pair C times pair N, meaning that they should have a higher binding energy. And this is also an observation. And don't ask me why, but this is the actual expression that could be used to fit this function. Okay, this is a fit value. Okay, you put everything in here. This is the numbers that you get. Okay, this is how do you get these numbers? Simply compare to the energy, the binding energy required for the different particles. You can measure that in nuclear reactions. Okay, so this is a pretty good model. Actually, you can. I don't know if this. Oops, no. This line over here, this should be points. So this line over here is a prediction. Okay, it's a theoretical prediction of what should happen to the different nuclei. Okay, it's not that perfect as this. You know, it's wider. Okay, it has a wider range because each of the nuclei, they are not necessarily on the line. Okay, so this is a model of a way to think of how the particles, you know, how the binding energy of the nuclei are changing as a function of the value of A. Okay, and you can see something like very important here. This is the electromagnetic energy correction, which is, it turns out to be a 0.71 term, which is very, very low. Okay, this number here, the initial correction turns out to be 15.75. If none of these numbers existed here, oops, no, where am I? Here, you know, this number should be 16.8, but it's not. It's 8 point something. Let's say 8. On average, you can think you have to be reminded that this thing goes up here from deuterium to helium-4, but you know, roughly this number is a flat value of 8 binding energy per nucleon in all the nuclei that exist. Okay, so that's typical binding energy of stable nuclei. Yeah, but the number 8 here, you know, this, what I'm trying to say is this number here should be 8 if none of these other corrections needed to exist. Due to the existence of this other correction, this turns out to be 15.75, which is a much higher number than the binding energy per nucleon. Okay. There's a different model that one can consider, which is the let me see how we do it on time. Oops. Okay. We still have a few minutes to go. So this is this is a model to describe the interaction of the nucleus inside the nuclei. So one can think of an approximate potential to describe the interaction between the nuclei. So this would be the interaction between nucleons inside the nucleus. This R here is of the order of the approximate nuclear radius, 10 to the minus 15 meters or something like that, or you know, 2 times 10 to the minus 15. That's this value. It is an attractive potential. That's why it goes down. And how deep does it go? So this is a particular nucleus. Then it goes something like, you know, 50 mega electron volts deep. Okay, that's what it is. And so this is an approximate function. And what can you think about this? This is why this model of the you can use this potential to actually solve the Schrödinger equation for the nucleons living in a potential like that. You do that, and what do you find? You find the radial Schrödinger equation. You separate the variables. You find the radial part. Of the radial part, you have to put a potential like this. This is a potential widely different to the potential you can see in electromagnetic interaction is what you see in regular atoms. Okay, now you have to replace it by this thing that is very attractive in a very small radius, and you know, it's very deep in energy also, and so it confines the particle of a nucleus to live in this very small energy range here. I'm sorry, in this very small spatial range here, R, okay? And the energies you actually need to deliver to these things are of the order of 8 electron volt per every nucleon. So the nucleons are going to be very well bounded here. Let's say you have a state with nucleons here, they are here. So what is the energy you need to provide for this guy? Well, on average, on all the nucleons, you need to provide almost 8. So essentially the energy of the nucleons would be around here, and if you give that energy to each of the nucleons, you can get them to look like a separate entities, essentially. Okay, but these particles that live in here, that live this is the radial part of the potential, but there's also the angular part of the potential. How's the angular part of the potential? It's exactly the same as the angular part of the potential that we saw in when we were solving the Schrödinger equation for an atom. Okay, you get the same structure, so the existence of angular momentum, the L square thing, it's valid here. The spin is also valid for each one of these particles. So this is why you get the orbital angular momentum of a nucleus here, which is valid. So you get a similar structure as you get for atoms. You get a shell model, meaning things that complete, and somehow they are more stable than others. Like, let's say, noble gases are more stable than, you know, fluorine, for example, you know, or beryllium, because the stability of the nuclei somehow has to do with that symmetry. Okay, and you can actually get some conclusions out of using the approximate potential felt by the nucleus inside the nucleus. Now, if for protons, the potential should be a bit different, because you have to actually include also the electromagnetic repulsion, and this is here in this color here. So for protons, the total potential for the protons will be the nuclear potential. It's the same one as felt by the neutrons, and that you have to correct that by the electromagnetic interaction that actually shift this curve a bit up. So the effective potential for protons is the one that is shown here with this line. You can see that around here there's no there's no interaction. I mean, there's no nuclear interaction. What are we seeing here is simply the potential, the electrostatic potential barrier. This is the potential between two charged particles. So this is why this guy is positive here, meaning it goes beyond the zero value, because the energy of two particles, you have to bring them from infinity, you bring them all together until you get to a point where the particles actually are feeling the nuclear force, and when that happens, they come down here. So two protons beyond the radius of the atoms actually interact with this curve here, which is the electromagnetic interaction. Okay, and this part here is the nuclear interaction, which is much stronger. Okay, this table to the right here, it's called a Segre stability plot. Okay, it shows a point for each one of the atoms that are stable in nature. These are in this total plot here, there are about 300. Okay, 300 points, but there are about, you know, between 2,500 or something like that known nuclei. The other ones that are not here are not stable. So that's the difference. These guys, we know them and they are stable. Okay. Let's see if I understand, if we can sort of put numbers here. This at the bottom here is the Z of a particular nuclei, and this is the neutrons of a nuclei. Okay. So and you can see this line here. This line here is the n equals Z variable. Okay, so in this line, the nuclei that are close to this line, they have the same value of n and Z. So you have let's say helium. Helium 4 is in this line because it has 2 protons and 2 neutrons. Okay. I think beryllium is not here. No, beryllium is not. Is beryllium 8 here? No. And that's it. Okay. So these are the different. These are the different nuclei that are stable. You have to note something. These lines here, for example, these blue lines, this is a value of constant A. Let's say you choose a certain nucleus that has a certain value of A, and only the values of A of a certain nucleus goes through the blue line. So let me see if I can show you here, for example.
Quick thing, not to interrupt, but I think we're a bit beyond schedule right now.
You okay? Okay, perfect. We can stop here. I could take this next time. Okay, thank you for letting me know. I'm sorry about this, man. We're gonna take this in a bit further during the next class. Okay. Okay, so I guess we'll see each other on Thursday. Okay.
Right. Take care, teacher.
Okay. Bye bye. You too, guys. Be good.